through MEGARA. So thank you, Jackeline. Away you go.
Yeah, thank you. As Quentin said, my name is Jackeline Suzett Rechy-García. I'm a postdoc working with Jesus Toalá. And now I'm going to talk about my last paper, which is titled Dissecting the Compact Planetary Nebulae with M2-31 with GTC MEGARA. And this work is in collaboration with my friends. You can find their photos and their name in this part. Okay, as we know, planetary nebulae present a big morphological variety, and this indicates complex material ejection processes, including the interaction between stellar winds with different degrees of symmetry and the action with the high velocity collimated outflows. And the morphological classification is based on an image. Therefore, this classification can be compromised by the image quality. Also, high dispersion spectra in H alpha and nitrogen 2 are used to find evidence of collimated outflows. So in my PhD, I studied planetary nebulae with round appearance. You can find their photos and the image in this part. And the appearance is round, a little ellipsoidal. But the most beautiful thing is not in an image, it's in the spectral observation, because in the spectral observation reveals material moving at high velocity. So for that reason, I propose call them spectroscopic bipolar nebulae. And this kind of object allows to prove the critical moment when the collimated outflow interact with the surrounding nebular envelope. In this work, we studied this planetary nebulae M2-31 using traditional techniques, optical image and long spectroscopic observation using Alfox at the node in La Palma, Spain. But also, we have a program that studied spectroscopic bipolar nebulae using integral field spectroscopy. Specifically, we use MEGARA. And MEGARA means multispectrógrafo en GTC de alta resolución para astronomía in Spanish. And this instrument, you can find here a model, a 3D model. This was done by INAOE. And also, this instrument has two modes of observations. The first one is large compact bundle IFU, is this. And the second mode is multi-object spectrograph. And for our case, we use the first mode, LCB, because this mode, considering with the size, that Martin said some hours ago, is especially designed to study spectroscopic bipolar nebula, because these nebula are very compact, no more than 12 arc-second, so they can situate in this fall of view. And also in this part is the different BPH, and we use a BPH that I circle in this part. So this BPH has the highest resolution. Well, we studied other planetary nebulae using MEGARA. The first case is HUBI-1. Montoro Molina gave us a talk about that. And with MEGARA, we found that this planetary nebulae located different pseudoslits. This planetary nebulae has a material moving at high velocity. So with MEGARA, we found that this material is a shale-like structure moving at 250 kilometers per second. And the second job that we did was to study this planetary nebulae, and also Martin gave a talk, a beautiful talk. Well, and now we have a new beautiful observation with another planetary nebulae. And this is a position velocity maps. And if you observe this emission here, moving at high velocity too, more or less 220 kilometers per second. And if we confirm that, this planetary nebulae it would be one of the highest velocity, but maybe in the future I'm going to talk about that. Right, return to M2-31. This is a compact planetary nebulae with an angular size of 4 arcseconds times 3.7 arcseconds, and this is located at a distance of 5.9 kiloparsec. And this planetary nebulae belongs to the group of spectroscopic bipolar nebulae. It has collimated a bipolar outflow with expansion velocity reaching 90 kilometers per second. And also, well, in previous work, I have found that M2-31 was a Wolf-Rayet central star in carbon-rich WC4-6. And if you observe in this color composite image, you can see that this material in this part and in this part here, so as you see my cursor, of course, this material we call not north and not south, and other material in the direction of southwest. Well, with Megara observations, we are able to get pseudo-slit using a QFITS view software. So the white square in this part is the observation that we have, and subsequently using this software, we located different pseudo-slits and build a position velocity maps or PV maps. So the slit at 10 degrees is along to the north at north and south. For the 50 and 60 degrees, this is along to the north at southwest. And for the 140, we put this slit in an intermediate position. So this is the position velocity map in the right image. This is in the nitrogen lines and in other emission lines. So in all PV maps, we observe two bright blobs at 190 kilometers per second, 150 kilometers per second, and 190 kilometers per second. And this emission here and this correspond to the north and south. And for the PV at 60 degrees, this emission here correspond to the north at southwest. And the velocity of this north is 80 kilometers per second with respect to the velocity system. I forgot to say the velocity system for this planetary nebulae is 170 kilometers per second. And for other emission line, but especially for carbon-2, we observe that the emission is more concentrated in the central zone. Well, that I said above was analyzing the observation in a traditional way. But now we present a more detailed analysis of the kinematic structure of M2-31. So using this technique, we found 5 kinematic components with different spatial extent. Okay, and the first row is the normalized flux with the different contours. And the second row is the velocity tomography. And each panel represents the 5 kinematic components. So the leftmost and the rightmost are the different spectroscopic outlook we call them. And this spectroscopic outlook show an average velocity of 220 kilometers per second and 100 kilometers per second. The second pair of kinematic component that we found is the inner shell that is in yellow and turquoise color. And this are moving at 180 kilometers per second and 140 kilometers per second. And finally, in the central part, disclose a pair of slowly expanding structures. For the cases of the carbon-2, we have that the emission that we observed in the previous PV maps, the emission is concentrated in the central zone, and this is smaller than the emission if we compare with the nitrogen-2. And also the expansion velocity is smaller too. So in order to understand these 5 kinematic components, we extract the contours from the flux map and overlay them in the M2-31 image in a verse scale. So these in red and blue are the spectroscopic outflow that we found. And the tip of the blue component coincided with the north and southwest. And for the case of the inner shell are in this position. And in the case of the low velocity component in black line. And finally, also the carbon-2 is in the central zone of this planetary nebulae. So this is a beautiful result. Well, finally, we studied the spectral type of the central star of this planetary nebulae. We studied. Thank you. We studied in the central star in the orange region, and this is the spectral type. And we found that the star exhibits the presence of the classic broad Wolf-Rayet features known blue bomb, red bomb. And this is a zoom of this emission line. But also with this spectra exhibit this line that we call violet bomb, but represent the oxygen 6 emission line. And this line is the key to reclassify our central star as double O4. And finally, we compute the chemical abundance in the green region. And you can observe the different parameters that we obtain, the temperature and the density, and this represent a young planetary nebulae. And finally, well, according to the helium abundance, this planetary nebulae is a type 2. But if we check the abundance in nitrogen or the ratio between nitrogen and oxygen, this planetary nebulae is a type 1. And well, in summary, this planetary nebulae, we found 5 kinematic components using MEGARA. First of all, is a pair of spectroscopic outflows, the inner shell and receding and approaching component, a low velocity component that could be maybe a other outflow or maybe a other disk or orthogonal disk. And finally, 2 nodes at north and south. And well, this is the first time that we did maps in the carbon-2, and we are assigned the spectral type. And thank you so much.
Okay, thank you very much, Jackeline. Yeah, I had a quick look at this source in hash while you were giving a talk, and yes, in fact, the Pan-STARRS data almost shows as much detail as you've got from the NOT images if you look at it in the different Pan-STARRS bands, and you can push the contrast, see all the knots, see all the outer shell, and see the inner bright part anti-aligned to the outer regions, and also the spectra that we have are also showing the Wolf-Rayet features, but then that was known to ACCA, so you've just reclassified that central star to a different type of Wolf-Rayet central star based on your better data from MEGARA. So anyway, very nice talk. So thank you very much for that. I see Adam Frank has a question. Adam, over to you.
Yes, thank you. That was a beautiful talk, and it really seems to show what IFS can do beyond normal methods or the older methods. My question is about your low velocity component. I mean, it seems to be toroidal. And so would it be possible to understand from this whether or not there's any rotation in that? You know, it was, especially when we think about our common envelope stuff, was that just ejection, or was this ejection of material that still had a reasonable rotational component?
Yeah, we are not sure if this, you can see my slides or not, because I don't know if I check.
Yes, I can see them.
Okay. So we are not sure. We are not sure if this low velocity component is outflow or a disk. The expansion velocity between both region is more or less 8 kilometers per second, but we are not sure. But maybe we need to do a model in order to modulate if this can constrain the material, and after the spectroscopic outflow throw to the poles, but I'm not sure about that.
Okay, thank you. It'd be interesting to find out though, because yeah, that's that beautiful toroidal component of that points to something in terms of its origin.
Yeah, thank you.
Yes, in fact, in the Pan-STARRS image, if it's the same orientation, which I think it is, then that exactly matches when you just look at high intensity pixels in that image, say in the G band, you actually follow that inclination precisely. And I believe I can also see two components. So that seems to be reflected as well in the light and not just in the velocity. Okay.
Yes, yes. Thank you.
Yezu, you have a question.
Yes, only to extend further what Adam was asking. I don't have the impression that this is a disk. The expansion, as Jackie said, is like between the two components is something like 10 or 8 kilometers per second. So our interpretation is more like it's like a waste. It's giving the shape of this planetary nebula more than a toroidal expanded structure. So this is what we think is.
Sorry. Yes.
So it may be swept up. It may have been something that has been swept up by a central jet and sort of a cavity has been blown out of it, but it's not really
exactly. I mean, the star is a Wolf-Rayet star of the oxygen type, so it's one of the most powerful winds. So it's something like 2,000 kilometers per second. So this is what's blowing the jets perpendicularly to this waste structure.
Yes. I forgot to say that, but it's true.
Okay, very good. Any other questions for Jackeline?
No, but maybe I have a question for Star Wars.
Go ahead.
Because he present a new software and we can use it maybe in order to study the different chemical abundance, not using other longest spectra, if using this software. Maybe I'm interested in that.
Thank you. Yeah, we can do that, definitely.
Yes.
I think there's many people interested in Stavros' software, including me. So,
yes.
Right, any other questions? Final questions for Jackeline? If not, well, last but certainly by no means least, we now have